So in today's lecture, we're going to briefly go over correlation functions with global symmetries and discuss how to bootstrap them. And this lecture will also be somewhat of a review of the last lecture, because the last lecture was over a month ago and it was in a different room. And the last lecture was really kind of the heart of the lecture series, where it was an actual description of how to bootstrap in practice. And so I think it's worth discussing that again, now with the added ingredient of global symmetries. Okay, so we're going to consider CFTs with a global symmetry G, and we can allow G to be a continuous symmetry or a discrete symmetry. So something like ON or say ZN, for instance. So let's go over some basic kinematics of correlation functions of operators in theories of global symmetry. So the usual one-point function is 0. We can consider the two-point function of a scalar field phi, which has an index I and some representation R of this global symmetry group. We allow it to be a complex field, so we want to take the two-point function of phi and phi bar. And so this is fixed by global symmetry as well as conformal symmetry that have the usual space-time dependence, as well as this Kronecker delta function taking into account the global symmetry indices. We also are going to want to know the two-point function of operators with spin. We can consider an operator with spin and some representation with representation index A now. We allow this to be spin L. In general, it's complex operators. We take the two-point function with O bar, with global symmetry index B bar. And then this guy, again, we can fix up to some coefficient, let's call it C, which would have these global symmetry indices A and B bar, and then everything else is the same as what you would get in the case of the global symmetry. So for simplicity, I won't write down all position dependence. Lastly, we are going to want to consider the three-point function of two scalar fields with global symmetry indices I, J, phi bar, as well as a spin L operator. Whereas in previous lectures, the reason why we consider this guy is because this is what's going to be related to the four-point function we will discuss in a moment. Where again, this index A is in yet another representation of global symmetry. And so similar to previous lectures, this is fixed up to some dynamical coefficient called the OP coefficient, which is this lambda phi bar O, delta L R, where R is the representation for this operator. And then we have the usual position dependence. I won't write out the full thing because it's the same as the non-global symmetry case. The main novelty is that you now have a tensor structure for this representation R, which has the various global symmetry indices I, J bar, and A. And then everything else is just various position dependence Z's, which is exactly the same as the case before. So, but the novelty is this tensor structure, which can be computed, as I'll discuss in a moment. So some comments we can immediately make about this three-point function is that all the representations in tensor products of R, so say this is in representation capital R, and so this would be in representation R bar. And so if you look at operators which are in this, like the tensor product of R with R bar, which is the operators that would appear in this three-point function, so you can choose a basis such that they are either real or come in complex conjugate pairs. And so that means we can choose these tensor structures such that the OP coefficients are related as follows. So phi bar, O delta L R equals the conjugate of lambda, phi bar phi, where we now move the bar to the first guy, delta L R. And then, if we want to move the bar back to the first one, this is at the price of having a -1 to the L factor. In general, recall from previous lectures that OP coefficients, if you switch around their labels, it puts a -1 to this bit. So what this implies, this factor implies that when the representation R for this operator O is real, the OP coefficient is real for even L and pure imaginary for odd L, while when the representation is complex, then the OP coefficients will come in complex conjugate pairs. And so this is important because once we discuss the 4-point functions in a moment, this will ensure that the OP coefficient squared will be positive, which is something which is important for the Bootstrap algorithm. There's two more 3-point functions we should briefly consider. So instead of having phi bar, we can do phi. So both in the same real representation, and with an operator O. And then this guy will have the OP coefficient lambda phi, so no bars. And then this tensor structure, IJA, and as well as a bunch of position dependence. And then you can also consider the conjugate of this guy. So phi bar, I'll just write this very heuristically, phi bar O. And this guy will have lambda phi bar O, tensor structure T R bar, IJ bar, A bar, as well as a bunch of position dependence. And so in this case, the representation of this O will be in the tensor product of R with R, instead of R with R bar, as we saw over there. And this implies that we can choose these tensor structures, T here and T there, such that this OP coefficient is the conjugate of that OP coefficient, which is kind of the natural thing. And so one thing that implies is that if the representation of this guy, little r, so if R is in the symmetric product or the anti-symmetric product of these representations, capital R, then this implies that the spin of this operator must be even or odd. And the reason why is basically a very similar argument is here.
Sorry, the last thing with minus 1 to the L, you meant to write phi bar phi O.
No, I meant to switch it. That's the whole point, is that you get this minus 1 to the L because you went from phi bar phi to phi bar.
Then you put a bar on that.
No. So like,
What do you mean? The third thing, the right-hand side versus the left-hand side is the same lambda, yes?
Yeah, I mean, that's why the statement is that this can only be true if the spin is, the statement is that, so when the representation is real, the OP coefficient is real for even L and pure imaginary for odd L. Oh, sorry, yeah, I guess there should be a bar there. Yeah, sorry. Yeah, there's a bar there, such that it's real or pure imaginary, depending on each case. Okay, and then whereas here, it's spins either even or odd, depending on this representation little r is in the symmetric or anti-symmetric product of capital R's. Okay, so with these details out of the way, we can now move on to the 4-point function, which is the main thing we care about. And so there's kind of two interesting configurations of 4-point functions of phi that we want to consider. So the first configuration is phi I, phi j, the bar, j bar, and then phi k, and phi bar L bar. And so this guy, as usual, it's going to be a sum over scaling dimensions and spins. It's also going to be a sum over representations, which lie in R bar. And then we're going to have a 4-point tensor structure, I, j bar, k, L bar. We're going to have this quantity squared as well as blocks. And then is the usual position dependence. And so the important point is that this quantity is real if we choose our basis correctly. And so in particular, it's important that you define this 4-point tensor structure as basically the contraction of the 3-point tensor structures defined here, which will make sure that this quantity is positive. Because if you choose some bad basis and this quantity might be negative, and then you wouldn't be able to do the bootstrap. And in general, the spins here can be either even or odd. Another configuration of this 4-point function, which it's useful to consider, is where we have phi I, and then another phi, instead of having phi bar, just phi here. And then we put the two bar guys here. And so for this guy, again, we sum over delta and spin. We sum over representations that are now in R cross R, not R cross R bar. And there's going to be a different 4-point tensor structure here. I, J, K, bar, L bar. A different OP coefficient, phi, phi, O squared. And then blocks. And the usual position. And so now, in this case, the spin will be even or odd depending on if this representation little r of the internal operator is in the symmetric or antisymmetric product, which directly follows from the statements about the 3-point function over there. And so for these 4-point tensor structures, these could be computed just using global symmetry. You don't need to know anything about conformal symmetry. And so in the case of continuous symmetries, you can compute these things in practice using something called a quadratic Casimir. You basically just look for the eigenfunctions of the quadratic Casimir. This is described in the exercises for the lecture notes, which everybody did, so everybody already knows how to compute these things. In the case of discrete groups, so then you can't use the quadratic Casimir. Instead, you can construct these things out of character tables, and this is described in the literature. So there's a paper I referenced in the lecture notes by me and various authors where we first discussed how to compute these structures for discrete symmetries. Another thing, just kind of for practical purposes, there's also this code out there called AutoBoot by Tachikawa as well as his student Go, which allows you to automatically generate these various tensor structures, although unfortunately it does not work for every group. So it only works for discrete groups up to a certain size, and for continuous groups up to a certain rank, and the rank is actually quite small. But at least for some basic examples, one can just use AutoBoot to generate these structures. You can also just compute it yourself using these two methods. This is basically character tables. And the important thing when computing these guys is just to make sure that you choose the right signs such that in your convention, this OP coefficient squared will be positive. Because that's the thing which is required to do the Bootstrap algorithm. Like if you screw that up, then you won't get the correct results once you start Bootstrap. Okay, so let's make some brief comments about conserved currents. So in previous lectures, we discussed how every local CFT has a stress tensor operator, which has dimension d, spin 2, and it would be in the singlet of your representation in G. So this is the stress tensor. If you have a continuous group G, then you have another operator called the conserved flavor current, which has dimension d minus 1, spin 1, and this would be in the adjoint of the group G. So this is called like the flavor current. And so this operator is for any local CFT. So local CFTs include most physical CFTs. CFTs that aren't local are generalized free field theories usually. So a generalized free field theory, even if it has a continuous level symmetry, nonetheless will not have a conserved flavor current, nor will it have a conserved stress tensor. In the cases where you have one of these guys in a local CFT, you can show, analogous to the argument for the stress tensor, that the OP coefficient of this current, which appears in, say, phi phi bar, so this guy is, in a certain normalization, just equals 1 over square root of Cj, where Cj is defined as the coefficient that appears in the 2-point function of canonically normalized currents. So the idea is that here, this is the standard canonical normalization you would see in a standard quantum field theory textbook. In this case, this is some non-trivial quantity you have to fix dynamically. In the Bootstrap, we renormalize this thing by square root of Cj such that this thing has unit normalization, and that pushes this dynamical factor Cj into the definition of the OP coefficient. And so this is how Cj is put into the Bootstrap in practice. This is analogous to what we saw with Ct before. Okay, so after this brief interlude, we can return to the 4-point functions. And so now we can just apply crossing to these 4-point functions as written in each configuration, where as usual the crossing we do is we cross the first guy with the third guy. And so the statement is that once you have a global symmetry, there's actually two non-trivial sets of crossing equations you can get by looking at each of these configurations. This was unlike the case where we just considered real scalars phi in the past, where there was basically just like one crossing equation you could get. So applying crossing to each of these guys for the first equation, it's going to give us this crossing equation summed over these operators, as well as representations in R cross R bar. We have the OB coefficient. We have this operator. And then these tensor structures are going to appear. So first for the S channel, these F's I'll define in a moment. They're basically combinations of the conformal blocks. And this is minus plus. Another tensor structure, which has now been crossed. So now it's K, J bar, I, L bar. So that's one crossing equation. And then the one we get from the second equation, it's actually two sets of crossing equations, because you can do it for plus or minus. And then from the second configuration, we can get another family of crossing equations, which this includes two kinds of representations. So from the S channel, you get representations that are in R cross R. And in that case, you get the OP coefficient lambda phi phi, magnitude squared. And you get this 4-point tensor structure, I, J, K bar, L bar, with one of these F's. And then in the other channel, there's a minus 1 to the spin factor, and then we get sums over representations in R cross R bar, because that's what the cross 1-3 channel is. It includes different representations. And that includes this OP coefficient squared, K bar, J, I, L bar, as well as this F factor. Okay, and so the reason why you get two different kinds of representations here is that when you cross this, this looks like something which is like this. It's like phi bar phi, phi phi bar, and that's the same kind of representation as the one you got in the first go. And so in practice what you do, okay, and then these F's finally are just defined as various combinations of cross blocks. So this is V to the delta phi, G delta L UV, plus or minus, U to the delta phi, G delta L, V, U. Okay, and so what you have...
Sorry, could you be a little clearer about what your indices are?
So these indices R, I, J, K, L are the ones that appear in these external operators.
So just the one, just the final definition there. That's F plus or minus with subgroup what?
Okay, so for this guy, it's I, J, K bar, L bar. And in this guy...
about the F.
Sorry?
Asking the indices of F.
Oh, F, okay, this is a scaling dimension delta. This is spin. This is the thing we're summing over here. So this is like, operators with spins, scaling dimensions, plus or minus, there's just two kinds of F's, because in one case you add a block to its cross version, in another case you subtract a block from its cross version. Then it's a function of U and V. And then delta phi comes from the fact that, when you do crossing, you multiply this x1, 2, x3, 4 factor on both sides, and that gives these factors of U and V. Is it good? Okay. Great. And so what you do after you have these two sets of crossing equations for some specific example, you would use your explicit expression for these 4-point tensor structures, which is just a bunch of numbers, and then you would just solve for the linearly independent combinations of these F's. I'll give an explicit example in a moment, because so far it's been a little bit abstract. And so after you solve that, what you would find is something, what we call the crossing equations, which would be, summed over the various scaling dimensions, spins, representations of various OP coefficients, squared, and then some crossing vector, V delta L R, where this V is some combinations of F's. And so so the idea is that you have a different crossing equation for each scaling dimension, spin, and representation. So you sum, so you sum over these, and then the number of crossing equations is correlated to the number of representations you have. So the general rule is the number of crossing equations you get corresponds to the number of representations that appear in this OPE, which have either even spin or odd spin. Although sometimes there's exceptions to this rule, but that's kind of the general intuition. So let me give an explicit example, which should make some of this discussion a little bit more concrete. So I'll do the simplest example, which is where the group is ON. And then there's other examples which are given in the lecture notes. So when the group is ON, then we can consider a basis of tensor structures, which are just going to be various Kronecker deltas. And we're also considering fundamentals. So phi is just going to be in the fundamental of ON. And so in that 4-point function, there's going to be 3 structures, which is basically this, as well as permuted indices. And so you can use the quadratic Casimir of ON to work out what the appropriate tensor structures are. What you find is that the tensor structure, okay, so first of all, if you're doing V, let's say V is the fundamental, so V cross V is going to include the singlet, as well as the traceless symmetric, as well as the antisymmetric, which is also the adjoint, what we call ST and A. And so the tensor structure for S, you find it to be just literally this delta ij, delta kl. The tensor structure for the adjoint is delta ik, delta jl, minus delta il, delta jk, where it's important the overall sign here. And then finally, the tensor structure for the traceless symmetric is delta ik, delta jl, plus delta il, delta jk, minus 2 over n, delta ij, delta kl. This basically removes the trace. And so this n is very important, because this is where n enters into the bootstrap in a very practical sense. And so the overall sign of these tensor structures, the overall magnitude doesn't really matter, because that would just change your normalization of the OP coefficients, but the sign does matter. Because if you change the sign here, for instance, then there would be a normalization in which OP coefficient squared would be negative, and that would screw up your bootstrap algorithm. So this is the one thing you want to be careful about. One way of checking this in practice is you would just expand free theory correlator in terms of these structures and check that you get positive OP coefficients. So this is what I usually do whenever I'm bootstrapping anything. So after using these explicit tensor structures in these formulas, you find that there are 3 crossing equations, which matches our intuition, because the singlet sector has even spin. The traceless symmetric also has even spin, because they're both in the symmetric product, whereas this antisymmetric guy has odd spin. So because you have 3 representations, each just with even or odd spin, that matches the intuition that you should get 3 crossing equations. And so in practice, the crossing equations you get, these V's, in the singlet sector, which has even spin, we write L plus, you get this vector of 3 crossing equations, 0, F delta phi minus delta spin, F plus delta spin. And then the V, which appears for the antisymmetric, which has odd spins, this is going to have F minus here, minus F delta phi minus delta L, and F delta phi plus delta L. And then finally, the last one is the V for the traceless symmetric, which has even spins. And so this guy has F minus delta phi, delta L, and then we get the independence. 1 minus 2 over n, F minus delta phi, delta L, and minus 1 plus 2 over n, F plus delta phi, delta L. And so, I mean, this independence came from this independence, and this is kind of the final place where n appears. And so these are the cross equations, which you will directly put into Bootstrap algorithm, and then you will change n in order to specify which ON you're looking at. And so actually, from this perspective, n could even be a real number, because it's just entering as a number here. It could be anything. It can be complex if you want. Now, whether or not looking at a real number or a complex number will give sensible results is a question. But at least, from the naive perspective, it's kind of trivial to analytically continue it. Okay. And so now let's discuss how to implement the boots. Okay, so any questions about global symmetries before we move on? Okay, good. So hopefully that was all clear. And so now let's discuss how to implement the Bootstrap, practically speaking. And so this is going to be a little bit of a review.
In principle, you will at some point encounter the fact that there are these n-symmetric, rank n and this symmetric tensor that is invariant with that.
Sure. Yeah. So if you look specifically at the 4-point function of fundamentals, then without further assumptions, that doesn't actually affect things. So like it would affect things if you made assumptions that, like, say you're looking at O4, if you made some assumption that the OP coefficient for the self-dual guy is different from the anti-self-dual guy. But like without making, but just like the naive, no assumptions fundamental 4-point function, it wouldn't affect it.
Right. I guess if you, in principle, if you go to 2 n-point function, what?
Yeah. There certainly are 4-point functions of operated into representations where it does matter. I'm just saying that in the most vanilla case, it doesn't matter.
Yeah, but I'm just trying to say that the Bootstrap crossing equations in principle should know about the integerness of n.
It knows about the integerness n in the sense that there could be special, representation structures for specific n's, n equals 4, etc. Although once you go to high enough n, I guess it's more complicated for it to actually tell the difference.
Yeah, but if you, in principle, you consider enough representations, right? Don't you run into a situation where you would encounter this?
Probably. Although, like, people have also written papers about how to define ON for a real n. I think there's a paper, by Slava and Damon, in some kind of categorical sense.
It's not supposed to be a standard unitary CFT.
Yeah. It's probably not unitary. Nonetheless, if you just naively do the bootstraps for real values of n, at least between 2 and up, you seem to get, plots that end
No,
up
but
continuing.
you're only looking at the
If you only look at the specifics of the correlator, yeah. If you look at mixed correlative systems, then you might actually be able to prove integerness of n, and that would be something very interesting to do. So I guess it's another question for the audience. Show integerness of n. Okay. I'll show some plots for the ON model at the end of this lecture. Hopefully we have enough time. But now I'm just going to go back and discuss how to implement the Bootstrap in general, even including global symmetries. So let's just review some facts about these 4-point functions we just considered. So the first fact is that when you're looking at a 4-point function, and let's say you're looking at the OP of phi and phi, so this includes, say in representation R and R bar, for instance. So this is going to include this kind of infinite set of operators, O delta L in representation R, which is in R cross R bar. And so we know we have these operators, and if it's a local CFT, we know it's going to have a stress tensor, and also if it has a continuous global symmetry, then it's also going to have a flavor curve. So it's one thing we know. Another thing we know is that the scaling dimensions obey bounds. So delta is greater than or equal to d minus 2 plus L when L is bigger than 0. And when L is 0, then delta is greater than or equal to d minus 2 over 2. So we have lower bounds on delta. We also know that we can choose some kind of basis where lambda phi bar, for instance, OP coefficient squared is positive. That's important. That's emphasized by the recent positivity conference. Finally, we know that these blocks, which show up in our 4-point function, in previous lectures we discussed how they could be efficiently computed in terms of these R native variables, where it basically ends up being 4R to the delta times some polynomial in R, which we described how to recursively compute using some variation of the homological recursion relation, which Slava once told me I should emphasize is actually the Davids and Coase recursion relation. Homological only did 2D. And so in this general formula, it's polynomial in R. It has this exponential in delta R dependence, and then this part is just poles in delta. And we know how to recursively compute all these guys. And so one statement about this is that if you multiply this side by a product of poles, as well as divide by 4R to the delta, and if you truncate this sum to be up to some R max, then this turns this thing into a polynomial. And so you just have some polynomial in delta, finite polynomial in delta. And so that's also important for the application we'll talk about in a moment, that you can efficiently express these blocks as polynomials in delta. And then finally, the most important point is that we have these cross-chaining equations we discussed before. So for instance, in the single correlator case, for simplicity, you have like this 4-point function g, was g of u and v, equaling v over u to the delta phi, g of v and u. And then for the global symmetry case, we have the various cross-street equations we discussed. And so these are kind of the ingredients we're going to use in order to do our algorithm. So I'm going to start by discussing the abstract algorithms, and then we'll discuss how to implement them in practice. And so I'm doing a little bit of review from the last lecture, so I'll go a bit quicker for simplicity. So firstly, we rewrite our crossing equations in general to be, this sum over delta LR of these crossing vectors v, labeled by delta LR, and this thing is 0. Remember, this v is just going to be a vector of f's, which are just crossed blocks. And so we can start by discussing the scaling dimension algorithm. So this is how to get bounds on scaling dimensions of operators that appear in the OPE. And so the four ingredients of the algorithm, first of all, we normalize a functional alpha. So we're looking at some functional alpha. And we normalize it such that when it acts on the v of the identity, then this gives 1. The second point is we assume that the scaling dimensions of all operators except for the identity are greater than or equal to some set of bounds. We have a different bound b for each spin L. So you're looking on a sector by sector of spins, and for all scaling dimensions for that spin. And then you search for functional alpha such that alpha acting on these v's, as labeled by delta L and R, is going to be greater than or equal to 0, except for the identity. And then finally, if such an alpha exists, then by acting with alpha on this crossing equation here, and if this is strictly positive and that's normalized to 1, that would give a contradiction. And so that gives a contradiction, which implies that this assumption must be false. And so in particular, if you make these bounds just be the unitarity bound, which is assumed, except for say spin 0, then that can allow you to carve out an upper bound in the space of delta phi versus say delta b0. So you would have some kind of plot looking like this. This is delta phi, this is delta b0, and then this would be the allowed region. And so this is the most general bound you can get without any further assumptions. You can add an assumption, which is called the gap assumption in Bootstrap literature. In that assumption, you insert you add an extra constraint, which is that alpha acting on a v for some specific scaling dimension, this is called delta star, for some specific spin star, and some representation r star. So you add this constraint that this thing is strictly positive, and you also make sure that this delta star is smaller than the bound which you chose on that spin. So basically you're inserting an operator below the bound. And then this is now an isolated operator because you've said there can only be scaling dimensions of this value and higher. Below that, there's just this one individual guy. And so then by doing some kind of grid over this isolated operator, you can then turn this upper bound, you can also get a lower bound. And so you'll get something like this. But that involves this assumption. Although, oftentimes this assumption will be justified. So for instance, if say you want to look at the icing model, you can assume there's just one relevant operator, that's part of the definition, and then just put a gap, say at 3 for the 3D icing model, insert an operator below, and thus get upper and lower bounds. And I will show explicit plots at the end of this talk demonstrating this fact. So that is...
so you add this condition.
Yeah. Sorry?
So that's the equivalent of this delta b.
Well, as long as it's lower than the delta b, because of course if it's above delta b, it's true. So the whole point is you want to insert some operator below your assumed gap. So there's one other algorithm, which is the OP coefficient algorithm. And so this is a slight variation of scaling dimension algorithm. So in this case, you normalize alpha, your function of alpha, such that alpha acting on a v for some specific operator, delta star, lambda star, representation star. So this equals s, where s is going to be plus or minus 1 for upper versus lower bounds. You'll see in a moment why one gives upper, one gives lower. Step 2 is exactly the same as before. And so you just assume that the scaling dimensions with a given spin are greater than or equal to some set of bounds, except for the identity and the specific operator delta star. And then step 3 is you now say that alpha acting on all these other v's, so this is again similar to before, is greater than or equal to 0, as long as they satisfy number 2. And then finally, in the last step, you maximize alpha acting on the identity v, for the identity operator. And when you maximize this, this combined with that crossing equation, so basically you turn that crossing equation into 3 terms. So one term is the identity, one term is the operator you're bounding, and one term is everything else. And so because the everything else part is strictly positive, and because the operator you're bounding now has coefficient either 1 or -1, that immediately leads to either an upper bound or a lower bound, depending on whether or not you chose s to be plus or -1. So in the upper case, you have the OP coefficient, lambda star, of your specific operator, squared, to be less than or equal to minus alpha of acting on v of the identity. And then in the lower bound case, you have lambda star squared being greater than or equal just plus alpha acting on the identity. And so the minus plus doesn't really matter. It just means that when you run this algorithm, in this case, alpha will be some negative quantity. In this case, it will be some positive quantity. And so the important conceptual difference between the OP coefficient algorithm and the scaling dimension algorithm is in the scaling dimension algorithm, we're just looking for the existence of a functional. Whereas in the OP coefficient algorithm, we are not only looking for the existence of a functional, but we're actually extremizing it. And so that's why it can be somewhat more numerically intensive. Also analogous to the scaling dimension algorithm, without any further assumptions, you can only get an upper bound. Because the upper bound involves the assumption that alpha acting on this is positive, whereas the lower bound involves the assumption that this thing is negative. But if you don't have any gap assumptions, this being negative would contradict this assumption. Because these general set of v's, there's some continuum of v's, and the continuum will go all the way up to your delta star operator, and so you can't have this thing be negative and that thing be positive. And so if you want to also get a lower bound, so this thing requires a gap. So this thing basically requires that your delta star be inserted less than the bound in that given set. And then you can get both upper and lower bounds. And so this is something which happens kind of naturally in the case of supersymmetric theories. When you have protected operators, the scaling dimension is fixed, they're separated from the continuum of long operators, and then you can just get both upper and lower bounds for free. So that's kind of one of the nice things about looking at supersymmetric theories with the bootstrap.
Can you go over again the logic with the gap condition giving the lower bound, not actually.
For the OP coefficient?
No, just in the earlier thing.
Okay, so I mean, the intuition of why you get that is just like for a physical CFT, if say you're looking at like CFTs which only have one relevant operator, there's going to be just like a finite number of those CFTs. There's not going to be a continuum of such CFTs.
I'm not asking about that. I'm asking about the actual algorithm. So because you're adding an extra condition on alpha,
Yes.
so your space of alpha is going to be more restricted, and you're going to, by design, get a weaker.
Okay. So
how does that turn into a lower bound?
Well, okay, so it's a two-step process. Okay, so in the first scenario, like you would be varying this delta b, and then you would get some kind of upper bound. And if this delta b were to be all the way up to 3, you would probably just get disallowed everywhere, because that would be implying that there's no relevant operators. And so that's why it's like 2 disallowed. But then by inserting an operator below that, it makes the region more allowed, and thus it goes from being completely disallowed to now having both an upper and lower bound.
I'm not understanding operationally how that what actually happens, because you're just putting more restriction on alpha, right?
Yeah, so the more restrictions on alpha, that means the harder it is to find an alpha, which means the lab region gets bigger.
That's right.
Yep.
So why does that lead to a lower bound?
Well, because it's a lower bound relative to having everything disallowed. So I think you're getting confused. Like, you have to compare, there's 3 different scenarios. Maybe I'll write the plots for each. So in one scenario, so in all cases, the x-axis is delta phi. So in the first scenario, the y-axis is like delta b0, and you get some upper bound, right? And in this case, this delta b0, let's say we're looking in 3 dimensions. Say this is between 3 and its unitarity bound. Okay, right? So here we get a nice upper bound. Now imagine that we make delta b to be 3, then we would just get disallowed. Because like this allowed region is always like smaller than 3, presumably for the icing. And so if we just look at delta b equals 3, clearly that's disallowed. So then in this second scenario, just everything's disallowed, at least within the regime we're looking at, below 3. So relative to this completely disallowed scenario, there's the final scenario where we add in this operator below 3, and then it goes from everywhere being disallowed to a region looking like this.
I'm just not understand where you're drawing now. Are you drawing delta D or doing something else?
I'm drawing the x and y-axis. Okay, so now this y-axis is what I call delta star. So in this case, yes. So let me be clear. So this is delta V0. This is delta V0. This is delta star.
Okay, so you're not drawing delta D then.
Yeah, but the thing which is related is that this plot looks exactly like this plot, except the lower bound has been carved out.
Okay.
Yeah, but operationally that's how it works.
Okay, maybe I just misread what I can't read what you're writing there.
Yeah,
You didn't mean to write delta D, you meant delta star.
I meant to write delta star. Sorry. Yes. Yeah, I should be more careful. You go from delta V to delta star. Great. Okay. So hopefully that's clear now. And so now, let's further move these guys up. Finally, talk about how to implement this in practice. So you have to do various truncations. So I'll briefly go over this. So first of all, you want to truncate the number of spins to be smaller than some L max. This is justified because, as shown in the previous lecture, Richkoff proved that the tail of this block expansion gets very small. So it can be bounded by r to the delta. And so if we look at some small value of r, then very high dimension operators contribute very little. And because spin is connected to dimension, thus it barely contributes to the formula. So that's the first truncation we do. The second truncation is when we expand blocks, we only expand up to some r max. In the definition of this block expansion we discussed before. The third truncation is that the cross equations are a function of u and v. This is some infinite dimensional space. And so we truncate that by looking at derivatives in z and z bar, where z and z bar are just related to u and v, of rv's. And so we can look at just various combinations of derivatives around the point where z and z bar is crossing symmetric. And so in terms of r and eta, this crossing symmetric point corresponds to eta being 1 and r being 3 minus 2 root 2, which is roughly 0.17. And so r is fairly small, which is why, again, the tail of the block expansion is small. And so after you do this truncation, now you have a finite dimensional space of functions you're looking at, which just basically depends on lambda, where lambda is the space of derivatives we look at. And then the final truncation is the fact that delta is a continuum. And so one way of approaching that is just...
What is r in your second?
R is in the definition of blocks. So up there we wrote down that we write blocks a function of r and eta. They're expanded in R, they're polynomials in R.
I'm not understanding your second right here.
Yeah.
So
yeah, when writing down blocks as a function of R, we write them as polynomials in R. So instead of being polynomials all the way up to infinity, we truncate it at some finite value. Yeah. That's so I wrote the R max up there. And so then, so for delta, you can either discretize it up to some delta max, analogous to what we did with spin, which would be justified for the same reason. But a better approach is that, as discussed before, you can multiply the blocks by some positive factor, which turns them into polynomials in delta. And then what you end up having is a set of polynomial constraints. So polynomial in delta.
Well, what's the point of truncating on cutting off on R? Why do you do that?
Well, you have to do that in practice. I mean, okay. So in even dimensions, we have some exact expression for blocks. You could just use the exact expression. But basically, if you want to write the derivatives of the blocks as polynomials in delta, then you have to truncate it.
You mean a degree? You mean the degree of power?
Yeah.
Not R less than. Well,
Yeah, that's what I meant there. Okay, sorry. Okay, so,
yeah, I read R less than.
Sorry. Yeah, so R max as defined above. Sorry. Yeah, I guess that was being a little confusing. I just mean that, when expanding the blocks, you only expand up to a certain degree. Okay. And so you take into account the continuum of delta by thinking this as polynomials in delta after multiplying by this positive factor. And so then the question is, how do you consider a set of polynomial constraints in delta? And so this is what we will discuss next. And so this is getting to the really kind of nitty-gritty practical implementation. So let's start by discussing PMPs, which are called polynomial matrix programs. So the basic object of a polynomial matrix program is a matrix of polynomials, as the name suggests. With these two labels, J and W, I'll give them an intuitive definition in a moment, a function of X, and this thing is some matrix of polynomials P, also labeled by P and W, as well as like their matrix indices. Now, for the cross-section equations we're considering so far, which is either for global symmetry or single correlator, but it's always a single correlator, just maybe with global symmetry, we can actually just restrict to the case where this is just a single polynomial. And so, or a vector of polynomials. But we don't have to consider a matrix of polynomials. That is what we'll consider in the next lecture where we talk about mixed correlators. So for simplicity, let's just consider this as just a single polynomial in X. And then the statement of this polynomial matrix constraint, so okay, first of all, this is notation. So this W goes from 0 to some capital W, and this J goes from 1 to some capital J. So these are just labels so far. And so the statement is that for some B, which is a vector of size W, the polynomial matrix constraint wants to maximize B0, which is the 0 component of B, plus this vector B contracted with some vector Y, where Y is size W. And then this is such that the 0 components of these polynomials, we call it P0, it's a function of X, plus contracting W between your Y and your polynomial, it's also labeled by Y, is positive semi-definite, which is what this sign means, as long as X is greater than or equal to 0. And then you do this for all J 1 to capital J. So you have a different one of these constraints for each J, and then you're contracting over W. So let's briefly say how these new variables correspond to what we have in our Bootstrap algorithm. So this Y here, so this corresponds to the functional alpha, which has labels M and N for the various derivatives of Z and Z bar that we take, as well as another variable I can call C, which corresponds to the fact that you have a vector of cross-section equations V, and you have alpha acting on that vector. And so C is the label of that vector. And so the size of W is basically the size of M, N, and C, with a slight caveat that we impose some normalization on alpha, and so that kind of kills one of the elements of alpha. And so that's also what leads to this B0 and this P0. That's just after kind of like fixing the normalization. But roughly speaking, this Y corresponds to your functional alpha. And then this label J, this corresponds to spin as well as representations. Because remember, in the Bootstrap algorithm, you have kind of like different constraints for each spin and representation. And so too in this algorithm, you have these constraints for every J. So the label J corresponds to spin and representation. And then finally, this P itself is then just each component of your vector of crossing equations. So just as the vector of crossing equations is a function of delta, when this thing is a function of X, you relate delta to X, and that delta corresponds to X plus delta BL for each spin. And so X being strictly positive then corresponds to delta being greater than the bound you assume on delta. So it's basically just shifting things. And so then you see, like with this dictionary, this polynomial matrix program is identical to the kinds of constraints we do in our various algorithms. Of like, alpha acting on the set of V's for spin dimension and R being greater than or equal to 0. Okay, so this is the polynomial matrix program. And then we want to rewrite this thing in terms of the final thing, which is called an SDP, because then that's the thing which we're actually going to apply our numerical algorithm to. So an SDP is called the semi-definite program, and basically it's going to differ from the polynomial matrix program, and then instead of having polynomials, everything will just be numerical matrices, because that is the easiest thing for algorithms to take into account. And so the idea is that we translate, okay, so let me first just write down the definition of an SDP. So there are actually two SDPs which are related to each other. One's called the dual, one's called the primal. So the dual is actually the more natural one. Sometimes a little bit confusing. So in the dual case, we want to maximize B0 plus, so I'm trying to use the same notation as much as possible. If I use any different notation, I'll explain what the new notation is. So we want to maximize this thing where Y, again, is some vector, but you want to maximize it over the space of some new matrix capital Y, such that P0, which has labels J, and now we evaluate X at a bunch of points K. I'll explain that in a moment. W is going to 1 to capital W, YW, PW, J, XK. So basically we want this thing to equal trace of some matrix A, I'll explain that in a moment, as well as this matrix Y. So this thing should be 0, such that Y is positive semidefinite. So in this dual algorithm, so the new quantities is Y, and basically Y and Y comes from your original set of polynomials P of X by introducing some matrix A. A is basically a matrix of symmetric polynomials, which allows you to turn a bunch of polynomials into just some numerical matrix. And so the precise definition is not so important, but like the point is that the rank of this matrix Y is the same thing as the rank of this matrix A, which is why it makes sense to take the trace of both of them. And then the way you do this conversion is you look at some set of K points. Okay, but everything else is the same as before. And then there's also the primal algorithm. So in the primal algorithm, you minimize B0 plus the sum now over JK, P0, JXK, Y tilde, which is now labeled by JK. So this is kind of like the dual space of the previous Ys. So Y tilde is an element of this dual space. Well, it's dual of the dual, so it's primal. And then there's some new matrix Y tilde, which is defined to be the sum of the A's, which have label J, evaluated points K, with Y tilde. So the sum runs over J and K. So the statement is that this thing is supposed to be 0. And then this is such that the sum over J and K of P, W, J, evaluated points XK, Y tilde, JK, plus BW equals 0, and that this Y tilde is also positive semidefinite. And so the statement of SDPs is that, like, if you can solve both the dual and primal problem, then they actually end up becoming the same problem. But the way you solve these things in practice is you start with some random point. So how do we solve this thing in practice? We start with the random point for the 4 variables, which is Y, Y tilde, little y, and little y tilde. So we start with some initial point, and then we do various Newton steps, changing these vectors, little y, and these matrices, big Y. And in each step, we basically try to satisfy these constraints to the greatest extent possible. So when you start with your initial guess, it's not going to satisfy these constraints at all. But then as you move along in the space of possible y's, you're going to get closer and closer to satisfying the constraints. And so, so let's just give a name to these constraints. So in the dual case, there's one constraint we want to satisfy, which is this guy. And so like you want this thing to be 0. And so let's just call this thing in general delta W dual, where it has the labels J and K. And so this thing in general will be non-zero, but eventually we want it to be 0. And then in the primal case, we have 2 constraints. One of the constraints is that Y equals this. So let's define this thing to be delta W primal 1, because there's going to be 2 constraints. So this is one thing we're trying to satisfy. And then the second thing we're trying to satisfy is this guy. So let's call this thing delta W primal 2. And so we eventually want to find values of these capital Y's and little y's such that these deltas become 0, because then you're exactly going to be saturating the constraints in the definition of this STD problem.
Does delta depend on the label K?
It does. You're saying that this delta?
Both
No.
of this and the one.
One of them does, one of them doesn't. So this one does depend on the label K. It depends on J and K. This one does not depend on the label K, because in this case you're summing over J and K. Because it's like the dual of the dual. You know? So it has different labels.
And then the choice of K was over some.
So, I mean, like, K is not choice. It's like, K is like when you're converting these polynomials into this matrix Y, it's like, there's just some algorithm of how you do that, and it involves looking at K points.
Yeah, but so K runs over some finite sets.
Yes, it runs over some finite. Okay, so in addition to trying to minimize these deltas, you're also, as I've just explained, you're maximizing this quantity, you're minimizing that quantity. So let's give this quantity a name. So this is what we call the dual objective. And then this quantity we're trying to minimize. This thing we call the primal objective. So I'll just write it as P obj. So we're trying to extremize primal objective, dual objective, while at the same time satisfying the constraints, i.e. minimizing these three deltas. And so that's what the Bootstrap is doing, starting with its initial point and then doing various Newton steps.
How are the points xk selected?
Well, I mean, they're selected based on how many polynomials you have.
Yeah, but it's just randomly added to each.
I think it's some canonical choice. I think there's some ideal choice, but yeah, I should double check the algorithm. Maybe there's some variation in choices you can make. Anyways, so you're starting with some y's. You're moving in the space of y's, and so you claim that when when the maximum of the primal deltas, and because there's two of them, so 1 and 2. So when the maximum of this is less than some number you enter, which let's call this like the primal error threshold. So this is some number you enter, and so you declare that when it's less than the primal error threshold, then you say this thing is primal feasible. Similarly, when the maximum of the deltas for the dual, so when these guys are less than some number you enter called dual error threshold, then you claim that it is dual feasible. And so the point is that in general, as you're varying your y, it could be dual feasible before primal feasible, one for the other, etc. If it is both dual and primal feasible, then you can furthermore try to minimize the difference between the P objective, the primal objective, and the dual objective. So that's if feasible. So if it's feasible for both primal and dual, then you can try to minimize this guy. So this is what's called the duality gap. So D gap. And then when this thing becomes less than a duality gap threshold, which is also some number you specify, then you say it's optimal. And when it's optimal, it means that you've just solved the SDP. So you've solved the dual problem and you've solved the primal problem. And so there's kind of two scenarios. So like in the scaling dimension algorithm, we're just trying to see if a functional exists. And so in that case, we basically just want to check if it's feasible. And so in practice, we want to check that it's dual feasible, because the dual problem is what's related to our Bootstrap problem. And we find that if it's primal feasible in that context, that means it will never be dual feasible. And so that means we just can't find a functional, which means the point can be allowed. Whereas if we do find a functional, if it's feasible, that means it leads to that contradiction, and that means the point we're looking at is disallowed. And so that's so in the scaling dimension algorithm, you only care about feasibility. In the OB coefficient algorithm, though, you're actually trying to maximize a quantity, remember. And so then you expect, as long as you haven't made any typos, that you're going to get it to be both primal and dual feasible, and then it's going to start extremizing this P objective, the difference between P objective and dual objective, and then this specific number is going to be the thing that's going to be your bound on the OB coefficient. So it's going to be so you're actually going to care about the value of the P objective and the dual objective. That's something you don't care about in the case of scaling dimension. Okay, so now let me give a practical demonstration in the remaining 30 minutes. Before I do that, any further questions? Hopefully this is reasonably clear, but the demonstration should make it more clear. Okay, so let us turn on this thing. Power projector on. So people can ask questions as the screen lowers, if they desire. Meanwhile, I will put the relevant stuff. So, as I mentioned before, if you look at the lecture notes on the archive, M, which is a wrapper that tells you how basically to generate input for the Bootstrap, which you then are going to run SDB on. So I won't go through the details of the wrapper. You could ask me about that later. It's basically just